Can you see my cursor?
Yes.
Okay. So it's a partition of the vertex set into k pieces, v1 up to vk, with the property that no edge of G joins a pair of vertices in the same piece. In other words, each vi is what is called an independent set in the set with no edges inside of it. And the question is usually what is the smallest k with which such a partition is possible, and it's called the chromatic number of G, denoted by chi of G. It's the smallest k such that G has a proper k color. Okay, so the title of my talk, infinite graphs are mentioned. So what about infinite graphs? I mean, these definitions make perfect sense regardless of whether the graph is finite or not. But in graph theory, most of the time we assume that the graph is finite. And there is some justification for this, sort of classical results that tell us that, maybe nothing really, at least of the number of colors that you want to use is finite, nothing really new and interesting happens, even if a graph is infinite. So an instance of this is the theorem of De Bruijn and Erdős from 1951, which says that if you fix k, a natural number, the number of colors you want to use, then, and you're given an infinite graph G, then G is k colorable if and only if every finite subgraph of G is k colorable. So of course, the one implication is clear. If you can color the whole graph G, you simultaneously color all of its subgraphs. But the non-trivial part of this theorem is that you can go back. As long as you know that every finite subgraph of G is k colorable, you can somehow glue those colorings together to form a coloring of the whole graph G. Which means that if you want to understand, which infinite graphs are k colorable, you really only need to know which finite graphs are k colorable. So maybe there is nothing particularly interesting having to do with the infinite graphs specifically. But I will try to convince you that actually there are still some interesting combinatorial questions about colorings in particular that you can ask that would only make sense for infinite graphs that somehow don't have counterparts in the finite situation. And the best way to explain this is by giving you an example. So here's a particular example. Let's try to work this out. This is going to be a specific infinite graph, this graph has some importance so it's not just an infinite graph that I thought of today when I was making slides. It's a graph that actually comes up in in other parts of math, especially in topological dynamics or ergodic theory. It has to do with dynamical systems. So, but the definition is very combinatorial. So first, I'm going to find the vertex set of the graph, and every vertex of my graph is going to be an infinite sequence of zeros and ones, indexed by the integers. So the vertices themselves are infinite sequences of zeros and ones, infinite in both directions, with the additional condition that the sequence is aperiodic. So what this means is that something like if I have some kind of a random sequence of zeros and ones, this is going to be a vertex in my graph. And I'm underlining this zero here to point out which of all of these digits is representing the zeroth entry of the sequence. So because it's infinite both ways, so it might otherwise it wouldn't be clear where zero is. So this is say the zeroth position, and then it's infinite to the left and to the right, and it's just some kind of sequence of zeros and ones. Except that I'm not allowing periodic sequences. So, for instance, something like this: 0, 1, 0, 0, 1, 0, 0, 1, 0, etc., etc. If it's just an infinite sequence that's a repetition of the same finite chunk, then this I'm excluding from the vertex. You will see in a moment why I want to exclude those. But if you just write a random sequence of zeros and ones, this is going to work. So this is the vertex set. Okay. Okay, does this make sense so far? Please, at any point, if something is not clear, just unmute yourself and shout at me if there are any questions. So okay, this is just the vertex set. I still have to define the edges, but already you see that the set is very, very much infinite. There are certainly infinitely many possible sequences that you can form. Before I define the edge set, I'm going to define this operation called the shift operation on the vertex set, which I'm going to denote by the capital letter S. So given the vertex X, so a vertex is again an infinite sequence of zeros and ones. S of X is another sequence that is obtained from the first one by shifting it to the left by 1. Yeah, so if I start with this sequence here and I apply S to it, then it's just, you see everything just got shifted by one position to the left. Or you can think of it as the position of which of these digits I think is x0 shifted to the right by one. So this was the 0th position. Now this is the 0. So everything got moved to the left. And of course, if I start with an aperiodic sequence and I shift it by one, it remains aperiodic. So if I start with a vertex, I still get a new vertex. Okay, and here's, okay, this is a typo. This should be S instead of T. So the edges are defined as follows. I just put an edge between every vertex X and its shift, S of X. Okay, so what does this graph look like exactly? Well, if I start with vertex X, I can shift it once to the left, and I get this S of X, and I put an edge between X and S of X here, right? Then I can shift it the second time, so I shift it to the left by 2. And then there is an edge between S of X and this S squared of X. There's the X shifted twice. There's an extra edge here. And then I can shift it 3 times, another extra edge, etc. Or I can go the other way. I can shift it to the right by 1, and there is again an edge. And I can shift then it again to the right, and there is an extra edge, etc. And now you can see why I wanted the sequence to be aperiodic. Saying that it's aperiodic means that if I shift it finitely many times, I will not get the same sequence back. In other words, the sequence of edges will not cycle around back to the original vertex I started with. It actually is going to just continue indefinitely with this distinct sequence of distinct vertices to the right and to the left, like this. So these dot, dot, dots are really 2 infinite paths, going to the right and to the left. Does this make sense? Any questions? Okay. So again, this is what I just said. Each connected component of my graph looks like this. Like a vertex X, this is what this connected component looks like. It's an infinite path, and it's infinite in both directions. In particular, maybe I should point out that this graph is definitely disconnected. So this graph has uncountably many vertices, because there are uncountably many sequences of zeros and ones. But every connected component is countable. It's a path. Looks like this. So there are really uncountably many components. It's a very disconnected graph, which is, again, maybe not something that we're used to when we work with finite graphs. Usually then you can just assume that the graph is connected to pass to an individual connected component. Well, here, each component is very simple, and it's the way the components are put together that's maybe the more interesting part of it. All right, but uncountably many components, fine. We still can ask what the chromatic number of the graph is. Actually, what is it? This is a question to the audience. What is the chromatic number of this graph? I think you would have to unmute yourself because I don't think I can see the chat.
Is it 2?
Yeah, it's 2, right? Because the graph is just a bunch of paths that are, disjoint from each other. And it's very easy to color a path with 2 colors. You just alternate the colors, red, blue, etc. Okay, so the chromatic number is 2. In other words, I can partition the vertex set into 2 subsets, red and blue, which are 2 independent sets. Right? Okay. Well, let me ask you a question now. So here's a natural sort of question that one may ask. And this is certainly a question that, again, as I said, this graph is relevant in dynamical system. And this is the sort of question that you would ask there. But I think this is a question that is natural, regardless of where you're coming from. Okay, fix such a partition. So fix the coloring into red and blue. Now, these vertices are infinite sequences of zeros and ones. I can pick one uniformly at random. So I need to determine, the sequence of zeros and ones. I just toss a fair coin for each of the entries of the sequence. And all of these coins are independent from each other. And if a given coin is heads, then the corresponding value is 0. If it's tails, then it's 1. Right? This gives me a random sequence of zeros and ones, infinite one. So this is my vertex X. Xi. With probability 1, the sequence will be aperiodic. It's not hard to see. So really, I will, with probability 1, get a genuine vertex in my graph, which is this sequence. What is the probability that this random vertex is red? For this given coloring. But pick this random vertex. What is the probability that it's red? I wonder, do people have a guess, maybe? Does somebody have a guess of what this probability should be?
One half.
I predicted that that's the guess. Yeah, it seems natural, perhaps, to say that the probability that the vertex is red and the probability that the vertex is blue both have to be equal to 1/2. Maybe it becomes sort of natural if you look at this picture. It really looks like half the vertices in each of these paths are red and half the vertices are blue, right? So what else could it be? Well, this is a very good guess, but unfortunately not quite correct. But the reason why it's not correct is because this is a trick question. The correct answer is not some number that is not 1/2. The correct answer is that this number is not well defined at all, and the question didn't make sense to begin with. And the reason is that, well, there's this issue of these color sets being what is called not measurable, which really means that somehow the probability, the value of this probability of a point falling in one of these sets, is just not a well-defined quantity at all. So maybe let me elaborate a bit on this. So again, we're asking what is the probability that a random vertex of the graph falls into the red set or the blue set, and then saying that it's not measurable. So this is exactly an instance of this of these phenomena that only occur when you work with infinite structures. So of course, in graph theory, we use probability a lot, but most of the time, because we deal with finite graphs, we only have to deal with finite probability spaces or discrete probability spaces. And this situation cannot happen there. This is never an issue. You can always say, what's the probability of this or that event, and that's always fine. But in our case here, the probability space is non-discrete, right? We're working with uncountably many possible values for x. There's a non-discrete probability space, and those have this weird feature that some subsets are so complicated somehow, so weirdly shaped, that it is impossible to consistently assign a numerical value to their probability. And those sets are called non-measurable sets. This is something that a person working in continuous probability always has to be on the lookout for, and try to make sure that every time you say that you're looking at the probability of some event, this actually is a measurable set you're looking at. So probability is actually well defined. So the existence of these non-measurable sets was observed by Vitali in early 20th century, and so the way to think about these maybe is that these are sort of strange pathological sets that are just too ugly to deal with by methods of probability theory. And in general, when you deal with probability spaces, you hope to avoid non-measurable sets as much as possible. What do I mean by this? Well, one thing is that you can never encounter one of these sets sort of in the wild. If you actually have written down an explicit definition of a set, the set is bound to be measurable. These really pathological examples that, in fact, any way of proving that they exist involves something called the axiom of choice, which is one of the accepted axioms of mathematics, but it's sort of the most notorious and suspect one somehow. And the reason is that it allows you to, well, prove the existence of these weird sets, but moreover, it proves their existence without actually telling you what they are. It's really a pure existence result, very non-constructive. There is, at least without some other assumptions, there is no way to actually write down some kind of explicit definition of one of these sets. We just know that they sort of exist, and one can stumble upon one if one is not careful, but you never, if you know a specific set, this specific set is not going to be like this. So the goal is to avoid them, right? Again, if you're a person working in ergodic theory and you study these types of graphs because you care about how they interact with the probability on the underlying space, knowing that there exists a non-measurable set with some weird properties, completely useless information. You don't want to hear about it. You want only to have sets for which you can actually talk about probabilities. And because we want to avoid them, this leads to this area that is called descriptive combinatorics, which consists exactly of these questions. What sort of combinatorial results can we prove about infinite graphs on, say, probability spaces or on some other spaces with some nice properties, while avoiding pathologies like non-measurable sets and things of that kind? So if I want a coloring where the color classes actually have a well-defined probability of a random point falling into the color class, how many colors would I need? These are the sorts of questions that Okay, I'm claiming that these sets are not measurable, and at this point, maybe this seems a bit mysterious to you, especially, this is somehow I'm talking about graphs, but then we're bringing all of this terminology from measure theory and analysis. This actually is not very difficult to prove, and I would like to give you a sketch of proof for this statement, partially because I want to demystify it a bit and show that this is not as far out there as it seems, and also because some of the ideas of this argument will reappear later in the talk, so I want to put them on there. Okay, so we have this again. We have our graph, our shift graph G, and we have this partition into two independent sets, red and blue. And we want to show that no matter what happens, these sets must be non-measurable. There is no consistent way of assigning probabilities to these two sets. Okay, well, suppose that they are measurable. So the proof is by contradiction. Well, okay, what is actually the measurement? What is the probability that a random point falls into the set R? And the thing is that if we know that this is a well-defined number, then indeed, as we guessed earlier, this number would have to be equal to 1/2. So this is the proof why that is. So x is this random point, right? This is a random sequence of zeros and ones. Then what can we say about s of x? Well, how do you obtain s of x? So you flip random coins for x, and then you just shift all of them. Well, the result is still just the result of flipping infinitely many random coins, right? You just change the positions in which you put each of the coins. So in other words, s of x is also just a randomly generated sequence of zeros and ones. In other words, x and s of x are just, the distribution of x and s of x is the same. So the probability that x falls into the red set is exactly the same as s of x falling into the red set, just because it's exactly the same probabilistic construction that gives you s of x. But on the other hand, x and s of x are neighbors in the graph, which means that it is never the case, if s of x is red, it must be that x is blue, which means that the probability of s of x being red is equal to the probability of x being blue. This is exactly the same event. That's why they have the same probability. And of course, a vertex is either blue or red, so the probability that it is blue is 1 minus the probability that it is red. And now we see that the probability of vertex being red is equal to 1 minus the same probability. So it's red, and blue is probability 1/2 because of this outcome. Okay. Does this make sense? Calculation. Okay, great. So on the one hand, we know this. Now I'm going to show that actually this cannot happen. It cannot be that both of these have probability 1/2. So let me introduce this notation. Let C of x be the color of x. So C of x is red if x is in R, and blue if x is in B. And I'm going to use this fact from measure theory called Lebesgue density theorem. So this is a general fact about arbitrary measure spaces, but we only need a special case here for our particular situation, and this becomes a particularly nice statement. It says that measurable sets. You can well approximate, you can answer the question of whether a random point belongs to a given measurable set with fairly high degree of confidence by only looking at a finite amount of information about that vertex. So what do I mean by this? So assuming that R and B are measurable sets, the following is true. Give me an epsilon that is bigger than 0. Then there exists some natural number t and some kind of guessing function that does the following. So I generate a random point x. Well, there is some color that it has, either red or blue, C of x. Well, in general, to know what C of x is, I need to know everything about x. I need to know the outcome of every single coin flip, and there are infinitely many of them. However, if I allow myself a small probability of error, I can do this by only looking at finitely many of those coin flips. So what I do is I look at only the values, the entries at the position -t plus 1, ... up to t. So there are these 2t plus 1 digits from the infinite sequence that I look at, and based on just this finite input, I guess whether the color is red or blue. So I have some function, this guessing function, that takes as input, these sequences of zeros and ones of length 2t, and it outputs a color, either red or blue. And this guessing function is pretty good. The probability that my guess based on this finite amount of information is incorrect, so the color is actually different from the color of the vertex x, is less than epsilon. And this can be arranged for any given epsilon. if t, by taking t to be large enough. Okay, so does this make sense? So somehow measurable sets have this weird feature that even though to know for sure whether or not a point is red or blue, I would really need to know all of the bits in this infinite sequence. But if I'm okay with making an epsilon error, being wrong epsilon proportion of the time, then there's only finitely many of those bits that I actually need. So this is I will not prove this. This is something that is proven in the measure theory or a real analysis course. But once you know this, it's not hard to finish the argument. So let's do this. So okay, take a really small epsilon and let t and this integer t and this guessing function be as in the Lebesgue density theorems. So I can predict what the color of a vertex is going to be by only looking at finitely many digits with high probability. So now I know that the probability that the vertex is colored red is 1/2. This means that the probability that I guess red must be at least 1/2 minus epsilon, right? Because of those 1/2 proportion of the time when the vertex is red, maybe I make an error. My guess is incorrect epsilon proportion of the time, but the rest of the time I actually have to guess red, right? So this function guess, when it's applied to a random sequence of length 2t, it has to output red with probability at least 1/2 minus epsilon. Okay, and now we're going to be clever. Take a really large odd number n. So, well, really large really means bigger than 2t. Why do I want it to be odd? Well, since it's odd, if I pick any vertex x and shift it n times, right? It means that x, the distance between x and this vertex as n of x in the graph is n, which is odd, which means that these vertices have to have different colors because the colors alternate along the path. So that's how I'm using that the number is odd. Okay, but on the other hand, well, so look at this is this infinite sequence. Call it x, right? I can look at what happens around 0 here. These, the digits from x negative t to xt. What happens when I apply my guessing function to this sequence? Well, I mean, it's red with probability. The output is red with probability at least 1/2 minus epsilon. On the other hand, look at this number n here, and look at the sequence around it. Go from n minus t to n plus t. Again, this is just a random sequence of zeros and ones. When I apply the guessing function to it, it's again is going to output the color red with probability at least 1/2 minus epsilon. These two random events are independent because this one looks at zeros and ones in this sequence and this one in this sequence, which means that the probability that both of them output red is at least the product of the probabilities. So it's 1/2 minus epsilon squared, at least, which is roughly a quarter, right? Because epsilon is very small. But what do these guess exactly? This guess here, when you look at this interval, is guessing what the color of x is. And it only makes the mistake with probability less than epsilon. And here we're looking at, if you shift this whole sequence to the left n times, right, then this will be around 0. And it means that this sequence is predicting what the color of Sn of x is going to be. Right? And again, this only makes an error with probability epsilon, which means that the probability that both x and Sn of x have the same color and this color is red is at least the probability that both guesses were guessing red, minus maybe the probability of error happening one or the other way. So it's 2 epsilon maybe. But if you make epsilon small enough, this is still positive. So there is a positive probability that x and Sn of x have the same color and the color is red. And yet I just said that x and Sn of x cannot ever have the same color. And this is a contradiction. All right. So this is a typical type of argument that one would use to prove lower bounds so, okay, just to wrap this example up, you can ask, okay, so you cannot get the coloring with measurable color classes if there are 2 of them. How many do you need? And it turns out you can show that actually there is a partition of the vertex set of this graph into 3 measurable independent sets, which is, the technical way to state it, this is, or the term for this is, you can say that the measurable, what is called the measurable chromatic number of this graph is 3. So the smallest number of measurable independent sets you need to partition the whole vertex set is 3. You can consider this a somewhat challenging exercise to the audience to find this partition into 3 three sets for which actually the probabilities are well defined. Let's see here. Yeah. Before moving on, let me just say this is just a slide with a few generalities, which are not very important, but it's just the terminology so that, when they make statements of theorems, at least written statements are correct. So in general, this is just one example of a graph. Of course, in general, we want to prove the general theorems about, classes of graphs with some properties. And well, for this, I need to describe to you what sort of infinite graphs we look at. And the most standard type of graphs to look at is what is called a Borel graph. And I will not will not define all of the terminology that's involved. But essentially, here's what it says. For a graph G to be Borel, there are two conditions that have to be satisfied. First, the vertex set of G has to be what is called a standard Borel space. Okay, why is that there? Well, we want to talk about, say, measurable colorings, right? To talk about measurable colorings, the vertex set has to be not an abstract set, but a probability space, right? So that you can actually talk about probabilities and measurability sets there. Otherwise, the questions don't make sense. So it seems to be that the broadest interesting class of spaces to consider is what is called standard Borel spaces, which I will not define to you, but essentially it just means a nice type of space. It's maybe the unit interval or the plane, or and just think of something that you would call a space, and its chances are it is a standard Borel space. So say the space of all sequences of zeros and ones that's from our previous example is also a standard Borel space. So it's anything on which you can talk about, say, measurable sets or anything. So just think nice. Standard Borel, think of this as a fancy term meaning nice space. And there is a second condition, which is that, okay, you know something about the space, but then there is a graph there, and the graph itself maybe doesn't interact with the space very well, and then maybe it's silly to expect that you can get like a coloring of this graph that respects the structure of the space. So there needs to be some assumption of how the graph treats the structure on the space itself. And the good assumption is to say that the edge set is what is called the Borel subset of the Cartesian product. So first, why is it a subset? Think of an edge as a pair of vertices. Every edge connects to vertices. So if you think of it as a pair of vertices, it really is, well, a subset of the Cartesian square of the vertex set, the edge set, right? Every edge is an ordered pair, and then the set of all the edges is a subset of this Cartesian square. And we want this subset to be what is called Borel, which technically means essentially countable Boolean combinations of open sets. But again, you can think of it as nice. Right, so we just say that open sets are nice, and then if you write some kind of countable Boolean combination of open sets, that is also fine. So a complement of an open set, i.e. a closed set, is also acceptable. Indeed, in the graph from before, there is a way of defining a topological space structure on the underlying vertex set in such a way that the edge set actually becomes closed. Okay, so open and closed are fine, but then also say a union of countably many closed sets is also okay, or an intersection of countably many open sets is okay, or what is it? A union of countably many intersections of countably many open sets, things of that sort. So any kind of countable Boolean combination. And really the intuition here is that the Borel sets are those that you can write down. If you can write down the definition of a set, it means that the set is Borel. If there is some kind of recipe for telling whether a given point belongs to the set or doesn't, then it means that the set is Borel. That's really the idea. So you have to be able to tell whether the vertices are adjacent in the graph or not, in some kind of explicit fashion. And that's what it means to say that the set is Borel. But yeah, there is a relationship between measurability, as we discussed before, and Borelness. Namely, a set is measurable if and only if it differs from a Borel set and the set of measure zero. There are these Borel sets, which are super nice, and then you can modify Borel set maybe on the set of measure zero. So you change a probability zero event somehow, and that might not already be Borel, but it's still measurable. And this is if and only if. Okay, so with this whole terminology, we look at the colorings of Borel graphs in which every color class is, say, a Borel set or a measurable set or has some other regularity problem. So this is just the general set. The technical details are not very important. It's just so that the words are there. Maybe before, oh yeah, some notation. So I'm going to write chi sub b of g for Borel chromatic number, meaning that the smallest number of colors you need, so that every color class is a Borel set. And chi sub m of g is measurable chromatic number, the smallest number of color classes you need, where color classes have to be measured. In some sense, the analogy may be that maybe makes some sense to people in this audience of what the difference between these two notions is like proving something for all graphs versus for almost all graphs. So here, in the Borel case, you need some kind of recipe that tells you what the color of each vertex is. And it gives you a proper coloring of the whole graph and works for all the vertices. And in the measurable case, you need also an explicit recipe that tells you how to color each vertex, but except that you can do something else on the set of measure 0. So it really colors almost every vertex, and you throw away a null set. Okay. So what sort of things can you prove? It's just a couple of slides with typical results in this area. Our goal is to prove or disprove various analogs of results in finite graph theory for these infinite graphs with the additional measurability of requirements. So, for instance, here's the theorem of Kepkris, Seletsky, and Todorchevich, which was one of it's really from the paper that kickstarted this whole subject. If G is a Borel graph of finite maximum degree delta, then its Borel chromatic number is at most delta plus 1. Max degree plus 1, isn't it? If you remember this example we had before, it was a graph where every vertex has 2 neighbors, exactly, because every component is a path. So maximum degree is 2. And I said that it has a coloring with 3 colors. Right, so this is an instance of that. It's a more general thing. For any finite delta plus 1 colors are enough. And you can ask, is this best possible? Can we get rid of plus 1, say? Well, it is, in some sense, for sort of trivial reasons, because a graph of maximum degree delta can contain a delta plus 1 clique, delta plus 1 pairwise adjacent vertices. And then, of course, you would need delta plus 1 colors, because you'll need to color every vertex in the clique with a different color. But we know that if we're dealing with finite graphs, or with ordinary chromatic numbers, then this is the only thing that can go wrong. This is the theorem of Brooks. If G is a graph of maximum degree delta at least 3, then its chromatic number, ordinary chromatic number, is at most delta unless it contains the delta plus 1 clique. So as long as this obvious obstruction isn't there, delta colors are enough. You don't need a plus 1. So this is Brooks' theorem again. Well, can we have a Borel version of this? Can I insert the word Borel before graph and the little letter b in the subscript to this chi? Unfortunately, no. In a very strong sense, this is a peculiar situation. It's a result of Marx. He showed that give me a natural number delta, I can find then a Borel graph of maximum degree delta whose Borel chromatic number is delta plus 1, so you cannot even shave off the plus 1 here. And the graph not only doesn't contain a delta plus 1 clique, in fact, it contains no cycles. It's a forest. It's an acyclic graph, and yet you need this many colors to color it if you want the color classes to be Borel. So this is kind of remarkable. Brooks' theorem fails the worst possible ways. Okay, well, what if we are not so greedy and instead of Borel we say measurable? So we are allowing ourselves to throw away a set of measure 0. But everything else has to be colored nicely. Can we do that? And turns out, yes. Once the entire difficulty of this theorem lies in dealing with a set of measure 0. If you don't care about sets of measure 0, you literally get a version of Brooks' theorem. So if G is a Borel graph, maximum degree delta at least 3 on the probability space, then you can color it with delta colors so that every color class is measurable unless it has a delta plus 1 clique. So just like Brooks' theorem, somehow here a set of measure 0 makes all the difference. And you can get rid of the plus because of it. Okay, so these are some typical instances maybe of the sort of thing you want to prove. Where Brooks' theorem is the theorem of combinatorics, and then you try to understand, can you prove something similar with the word Borel or the word measurable thrown in for these infinite graphs. Okay, are there any questions at this point? So let me now change gears a bit. So I've been talking about infinite graphs so far. Now let me talk about distributed algorithm. This is a different sort of questions that you can ask about colorings or combinatorial questions in graphs. Now everything is finite. We're returning back to the finite world. And this is what a graph looks like to a person working in distributed computing. Every vertex is a little computer, and the edges are some kind of connection links between them. And the goal is maybe still the same. Find the proper coloring of this graph. So you want to assign a color to every vertex, in a way that adjacent vertices have different colors. The thing is that this is a decentralized network. So really, it's not like we look at the whole graph and decide which color every vertex is going to have. Every vertex has to decide for itself what color it is going to have. And these decisions have to be consistent with each other. So adjacent vertices have to choose different colors for themselves. But each vertex has to make a decision on its own. The problem is that the vertex doesn't actually know what the graph looks like. The only thing it sees are its immediate neighbors. And it can send messages to them and receive messages from them. And the question is, how many of these how long is an exchange of messages that is necessary for each vertex to decide which color it has to have, or is going to have, in a way that's consistent across all the vertices in the graph. Okay, so to be a bit more formal, we are working with what is called local model of distributed computation, and it's always stylized like this in all capitals. I'm not entirely sure why. It's not an acronym. It's just, I guess you have to say it very loudly when you read it. Here's the model. We're working on an n-vertex graph G, undirected and simple, and we think of each vertex as representing a processor or an entity of some sort, with edges representing communication links between them. The computation proceeds in rounds, and during each round, the vertices first perform arbitrary local computations. So there is no complexity restrictions on these local computations that the vertices can perform. We imagine that each vertex has access to unlimited computational power. And then they simultaneously broadcast messages to their neighbors. So every vertex in the graph simultaneously sends messages to all of their neighbors. And at the end, after some number of rounds, like this, each vertex must output its own part of the global solution to whatever problem they're trying to solve. In other words, its own color. Or if we're talking about edge colorings, then it has to decide the colors of the edges, or something else. And the complexity of such an algorithm is measured by the number of rounds required. We don't care about how complicated the local computations are. We don't care about how long the messages are that the vertices send to each other. The only thing that concerns us is how many rounds are needed. You might observe already at this point that there's something lacking in this description. Imagine that the graph is, say, the complete graph on n vertices, right? It looks every vertex runs the same algorithm, so it looks exactly the same from the point of view of each vertex. How are they going to decide which is going to get which color? Right, that's problematic. So we need some kind of symmetry breaking mechanisms that allow the vertices to distinguish between each other. And there are two standard approaches for symmetry breaking. There is something called deterministic version of the local model. In this deterministic version, each vertex originally, from the beginning, is given an identifier, which is a sequence of logarithmically many bits. And all of the sequences are guaranteed to be distinct from each other, which is possible, of course, because there are n vertices, so there are many different identifiers for all of them. And the algorithm has to work regardless of what the assignment of identifiers is. So the only thing, originally the vertex knows its identifier, maybe the identifiers of its neighbors. Then it can communicate with them somehow, get more information, and eventually has to decide what its color is. And the resulting coloring has to be proper regardless of how the identifiers were assigned to begin with. And there is also a randomized version in which instead of these identifiers, we allow each vertex is given a random number generator. So each vertex can create an arbitrarily long finite sequence of independent uniformly distributed random bits. And the randomness is independent for different vertices. So, of course, because it's now randomized, it's possible that all the vertices just so happen to generate exactly the same sequence of bits, and then there's still no symmetry breaking. But we don't require the algorithm to succeed every time. It just has to succeed with large probability, where the standard threshold is the probability has to be at least 1 minus 1 over n, or sometimes 1 over some polynomial. But this is so the probability of error for this algorithm has to be less than 1 over n. And you can see that, for instance, randomized model is stronger than the deterministic one because each vertex can generate just a sequence, or a random sequence of logarithmically many bits, and the probability that any two of them coincide will be less than 1 over n. And then you can use those sequences as identity. Okay. Does this make sense? So let me give you maybe some example. Oh, before doing that, like, why is this called a local model? The idea is that after t rounds of computation, a vertex cannot really know about anything that happens outside of its radius t neighborhood in the graph. Right? In one round of computation, it can only communicate with its neighbors. In 2 rounds, with its neighbors and their neighbors, etc. But it cannot go farther than t, distance t in the graph. So you can really think of this algorithm as a function that takes as an input the isomorphism type of the radius t ball around each vertex. And okay, this extra information, like the IDs of the vertices involved, or the random bits in the randomizer. And it has to, based on this information alone, it has to output the color for this vertex. And this function, if you apply it at each vertex of the graph, has to produce a proper color. So because of this, every problem can be trivially solved in big O of diameter of G rounds, just because every vertex can communicate with everybody else. So it's really, this communication is not an issue anymore. It's allowed to go all the way to the diameter. But so usually you want to do something smaller than this, and there are some standard benchmarks, like something polylogarithmic in there, or just logarithmic, or maybe sublogarithmic in the number of it. And this somehow is the, is the best thing, because this means this is always less than, essentially, typically less than the diameter, at least in the bounded degree. All right, so let me give you an example. I claim that if I want to color a path of length n with 2 colors, I cannot do this in less than n, in little o of n rounds. Say in the deterministic setting. Okay, here's the sketch of a proof, literally a sketch. Here's a path of length n. Suppose that I have such an algorithm. So each vertex looks at its radius, radius little o of n ball around it, and it makes a decision of what its color is going to be based on the information there. Well, because it's little o of n, I can fit 3 of these at least in my path disjointly. In fact, I can take this one at some odd distance and this one at some even distance from the original. Now, because this distance is odd and we're coloring the path with 2 colors, these have to have different colors, whereas this and this have to have the same color. Just because this is a 2 coloring, the colors alternate. But that's a problem, because whatever, say, the identifiers were in this interval and this one, I told you that the algorithm has to succeed regardless of exactly how the identifiers are assigned. So I can just switch the assignment of identifiers on this interval and on this one. Now this vertex will output whatever color this one was outputting, which was the same as this, so these will not be different anymore. And this is a problem. This algorithm doesn't work. So of course the issue here is that the 2 coloring is a very non-local problem. Once I set what the color of this vertex is, it somehow influences the color of this vertex that's really far away. Now we know that this vertex should only be looking at its small radius ball around itself. By the way, just for some sense of closure, if instead of 2 colors I allow myself 3 colors for a path, then you can there is a very efficient deterministic local algorithm. It works in big O of log star n. Log star is iterated logarithm. So this is like the inverse of the tower function. Is how many times you need to apply the log function to n to get something that's less than 1. So this is really tiny. This is much less than log n. So now why did I give the sketch of proof here? Because this picture here should be eerily familiar at this point. It's quite similar to the picture that occurred quite a back later when I proved that this graph, infinite one, where every component is a path, does not have a proper 2 coloring with measurable set. And at the end of the day, I had to draw a picture that looked very similar to this. There's the path, and something is happening at some interval, and then there is a disjoint interval somewhere else in the path, and then they can control what happens in the 2 intervals independently of each other, and that leads to a contradiction. So it looks very similar. And in general, when you look at these two areas, the types of arguments that are used to prove results in descriptive combinatorics and in distributed computing are often really similar to each other. Or somehow the difficulty that one has to circumvent is often very similar to each other, even though the settings are very different. And it's not only that the techniques are similar, the results also sort of parallel each other, you can observe. So, for instance, suppose we're looking at graphs of maximum degree delta, where delta is a constant independent of n. How many colors do I need to color such a graph with an efficient local algorithm? Well, I can do it really efficiently with delta plus 1 colors. That's a very old theorem, and the attribution might not be. I think this is the first time where this appeared more or less explicitly, but this is hard to attribute this properly because it's too old. The model wasn't really defined yet. But one way to interpret the result is that there's a deterministic distributed algorithm for delta plus 1 colorings of max degree delta that works on this iterated logarithm number of rounds. So really small. What about a Brooks theorem type of result? Well, there is a problem. If we want a deterministic algorithm for delta coloring graphs of max degree delta, even if they are acyclic, it's impossible to do this in less than log n rounds. So sublogarithmic becomes impossible. Yet, if I want to randomize such algorithm, then I have literally a Brooks theorem type of result. If delta is at least 3, then there is a big O of log n squared. Okay, whatever this function is specifically is not important for me right now. The point is that it is little O of log n. There's a little O of log n round randomized distributed algorithm for delta coloring graphs of max degree delta if they don't have delta plus 1 cliques. So this should remind you of that slide I had with the results of this type for infinite graphs. There are Borel colorings with delta plus 1 colors, no Borel colorings with delta colors even for acyclic graphs, and yet there are measurable colorings with delta colors for graphs without delta plus 1 cliques. So there's this correspondence where deterministic corresponds to Borel and randomized corresponds to measurable, and things seem to line up pretty well. And there is, the sort of main result I've been leading towards in this talk is that actually there is a reason why these things line up pretty well, is that because there is an implication between the two. It turns out that, in fact, if you know that there is a efficient distributed algorithm for something, then you can turn this into a result in this weird area talking about infinite graphs and measurable sets and things of that kind. So here's the result is more general, but this is a relevant special case for this talk. So fix the number of colors, say k, and let the fancy G be a class of finite graphs, okay, which for technical reasons I'm going to assume is closed under adding isolated vertices. And you can think of G as being, say, graphs of maximum degree at most delta, or triangle-free graphs, or acyclic graphs, things of that sort. Some kind of class of graphs, finite graphs that you're looking at. And suppose that you have a result in distributed computing. There is a randomized local algorithm for coloring n-vertex graphs from this family using k colors in little O of log n rounds. Okay? Say, these are graphs of maximum degree at most delta, and you can color them using delta plus 1 colors deterministically in little O of log n rounds. Then, once you know that there is such an algorithm, you can actually conclude that for any Borel, now given an infinite Borel graph of finite maximum degree, all of whose finite subgraphs, finite induced subgraphs, happen to be in this class, this graph, if the original algorithm was deterministic, its Borel chromatic number is at most k, and if it was randomized, its measurable chromatic number. So you can use these algorithms designed for finite graphs to obtain results about infinite graphs in this setting. And deterministic corresponds to Borel, randomized corresponds to measurable. Just in the remaining, 3 minutes. Okay, other questions about this. So this is kind of an interesting phenomenon that this area of computer science that is completely independently developed for computer sciencey reasons actually has direct applications in questions that are inspired by problems in analysis or dynamical systems, something completely unrelated somehow. And just as an example, I just want to sketch an application. Just a single one, but there are many. The point is that once you know this, of course, you can just go through the literature in distributed computing, find whatever coloring problems have efficient distributed algorithms for, and just translate them using this machinery into results in descriptive combinatorics about infinite graphs. So here's just a neat example, which I thought I should mention. So remember, we have Brooks' theorem and measurable Brooks, right? If a graph of max degree delta doesn't have a delta plus 1 clique, then its measurable chromatic number is at most delta. One way to state this, another one, since we know Brooks' theorem, is to say that if G is a Borel graph of max degree delta, at least 3, then its measurable chromatic number is at most delta, if and only if its ordinary chromatic number is at most delta. Because both things happen exactly when the graph doesn't have a delta plus 1 clique. So these are literally the same. This adding the measurable doesn't change the question in this situation, as it happened. Well, for what other values of the number of colors is this true? What about delta minus 1 colors? Can you still prove such an equivalence? And it turns out that you can, and in fact you can go quite a bit below delta, assuming that delta is large enough. So there is some lower bound, constant delta 0, so the following property. If G is a Borel graph of max degree delta and please delta 0, so it's not 3, but like 10 to the 10, but still a constant number. So if it's sufficiently large maximum degree, then if you take the number C that's less than roughly root delta, then the measurable chromatic number of G is at most delta minus C, if and only if its ordinary chromatic number is at most delta minus C. So you can subtract up to root delta from if you want to subtract up to root delta from the number of colors, these are literally the same questions. Measurability doesn't change. How to prove this? Well, here's the complete proof. Balmas and Esperet have a paper that in turn is based on the result of Molloy and Reed, in which they show that if you look at the if you're given a finite graph of maximum degree delta, and you want to color it with delta minus C colors, then where C is at most root delta, minus 5 over 2, then such a coloring if such a coloring exists, it can be found by a distributed algorithm that works in sublogarithmic number of rounds. A randomized distributed algorithm running in little o of log n rounds. So you can determine, in fact, you can determine locally whether such a coloring exists, and if it does, you can find it in such a short time. And now by this other theorem, this immediately tells us that if such a coloring exists, then you can make it measurable. So you don't need to do any extra work. And I maybe should say that this bound here, this funny-looking square root of delta bound, is almost sharp. You cannot replace it by square root of delta minus 1/2. So really, the threshold for this equivalence to be true is, somewhere between these two values, which are very close to each other. But a bit annoyingly, we don't actually know where the precise threshold is. All right, maybe I'll skip this application. Just a few final remarks. So there are two things to prove in that big theorem. Something about deterministic algorithms turning into Borel colorings. This is reasonably straightforward. And randomized algorithms turning into measurable colorings. This is actually somewhat complicated. And in particular, it involves the recent breakthrough work of Fisher and Ghaffari, Harris, and Kuhn, concerning distributed algorithms for the lowest local length. I'm just saying these words. It's kind of. I just want to emphasize that the randomized algorithm is much more the randomized side is much more complicated. Also, the natural question is, can you go back from infinite graphs to algorithms? And but the answer is, well, sometimes under some special assumptions you can, but not in general. In general, it seems that the question, like measurable colorings, is a strictly weaker type of thing to ask for than having an efficient randomized algorithm, for example, in the local. That there has to be some kind of, different, maybe somewhat different setup on the algorithmic side that would actually be equivalent to, say, having a measurable coloring. It seems that such a thing is possible at this point, and but I don't know what it would be. And in general, exploring these further connections between descriptive combinatorics and infinite graphs and computer science on the other side sounds like a promising line of research to take. And that's all. Thank you.
Thank you, Anton. So how do we clap hands in Blue Jeans meeting?
Yeah, exactly. I think that people can just unmute themselves and clap.
That's right. Great.
That's the most rewarding, at least, for the speaker.
Do we have any questions? I was going to ask what what's the opposite direction, but you asked it and answered it at the end.
Yeah, so I didn't say what the special assumptions are under which you can go back. It's a bit, it's a bit too much of a sidetrack. I can tell you later.
Okay.
But in general, like in full generality, there's definitely no converse with the theorem. So there are situations where there is a measurable coloring, but you can show there is no randomized algorithm running in little log n. But maybe, it feels like there should be something else. Like there has to be a way of relaxing the notion of the local algorithm to make the correspondence complete.
All right. Any questions from the audience?
So you stated just a special case of your theorem, right? So what is the most more general statement?
Yeah, let me go there. Yeah, here. Yeah. So the thing is that, well, there are several things that you can generalize in this statement. So one is that I'm talking here about just proper colorings, but you can consider other type of questions like edge colorings, or maybe a coloring with some extra property. Star coloring or something like that. The point is that actually this whole theorem is true for a broad class of coloring problems, which are in distributed computing, they're called locally checkable labeling problems. Really, the main condition is that you want some kind of coloring with the property that there is a uniform, some fixed bound, such that to tell whether a coloring of the whole graph is correct or not, you only need to check what goes on in this bounded radius balls around each vertex. So say for proper coloring, you only need to know what happens, you need to look at each vertex and its neighbors and see whether or not it has the same color as its neighbor. So it's radius 1 in that case. So in general, if there is like some number like 100, and the correctness of the coloring is verified by looking at balls of radius 100 in your graph, then this is what is called a locally checkable labeling problem, or just local coloring problem, whatever you prefer. And instead of proper coloring, you can use that in this statement. So that would be a generalization. You can also, another thing is that you can also say something about even if it's not little O of log n, but say just big O of log n rounds, there is still some useful information you can extract from it. If say it's a big O of log n here, then maybe this conclusion will not hold for all Borel graphs like this, but for all Borel graphs of sub-exponential growth. You look at your graph and you look at the sizes of, you look at how many vertices are at distance 1 from a given vertex, 2, etc. This is some kind of function of the distance. And, in principle, it can grow exponentially, right? And even the graph of bounded degree, like in a tree, it grows exponentially. But if it grows sub-exponential, is bounded by it's not a lower bounded by any exponential, then you can relax this little O to big O. Care about that sort of thing. Like maybe if you care about colorings of grids, for instance, a square grid is a graph of sub-exponential growth. But this is another direction.
All right. More questions? So if any of you interested in this topic, should talk to Anton, and perhaps you can find Anton could give you a couple of papers to read, and you can present in the working seminar. All right.
Yeah, I definitely have some interesting things in mind that interested people can look at.
Okay, great. That's great. So, all right, let's thank Anton again. All right, so now we know how to clap.